Hey guys, welcome back to AP Precalc. This is lesson 1.14. Let's get right into it. All right, so here's the bell ringer for today. Pause the video now if you haven't done so already, because I am about to go over the answer. So which of the following scenarios would best be modeled by a quadratic function? Remember, quadratic functions are going to be functions where there's either a pretty clear maximum or a minimum, or functions that are talking about area in terms of story problems. So taking a look at A, evaluating the number of Instagram followers based on their following. This is probably going to be linear, I would say. The more people you follow, the more people you're probably following. B, evaluating the volume of a water balloon based on how big the balloon is. Remember, volume is related to a cubic function, so it is going to appear cubic. C, so B is cubic. C is talking about evaluating shoe size based on age. Here, as we get older, our shoe size is probably going to go up, so this is going to be more linear. And then D here, evaluating the area of a fence based on how much fencing you are given. This is going to be probably quadratic because it's talking about area, so D is our answer here. Now today what we're going to look at is function modeling and applications of that. So the idea of modeling or regression, which is finding basically the line of best fit with a set of data, is a major component of the AP Pre-Calc curriculum, and we will revisit this lesson over and over again in different types of functions that we work with. This topic right now will utilize the graphing calculators heavily and often include story context, meaning I'll give you a story problem with a little bit of context rather than just giving you random data points and say, here, find the line of best fit. In Unit 1, we'll typically work with just polynomial functions for now. You won't really work with rational functions in terms of story problems because there's not a whole lot of story problems that are applicable to rational functions that we're going to see in this class. So basically, just think of this as like learning about lines of best fit, right? If we're given a set of data, boom, 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 and we want to find the line of best fit, that best models that data. All right, so building a regression model requires two steps. They're so easy. First, you just got to enter the data, right, into the calculator, into Desmos. So that's what we're going to be using today. And then the second is just choosing which model. This is right now going to be either linear, quadratic, potentially cubic, or quartic. And typically we will give you what type of model to use, or it would be pretty obvious based on the data which type of model to use. So here, finding a linear regression line for the following data. Read these steps here, try it in Desmos, and I have a video now to go over these steps exactly. All right, so to build this regression line, what we're going to do is first we want to enter the data that we need to be modeled, and then the second step is selecting our regression model. So first we want to enter this data by pressing this plus or this add item, and then we are going to add a table, not an expression. Once we have our table, let's enter in our data points. So we have our x coordinates of 1, 2, 3, and 4. And then we have our y coordinates of 5, 7.1, 9.3, and 10.9. Once we have this, then we want to find the best linear regression or the best linear line of best fit. So we're going to hit this add regression, and then it pops up linear, but you can choose whatever regression you want. Right now, we're just going to stick to linear, quadratic, cubic, and quartic. We'll get to exponential, logarithmic, and sinusoidal regressions later in the year. Here we just want linear, so we'll keep it as that. And this should be our linear equation, which is already graphed, which is y equals 1.99x plus 3.1. So that is our equation there. All right, so with that being said, now that we know how to graph or find our linear regression line of best fit, let's try example 1. Here we are looking for three things. We are looking for just our linear regression equation, and then we want to plug in our x value of 10 weeks old, figure out what is our y value here, and we also want to plug in a y value of 5.3 kilograms, and we are asked about our x value there. So this next video is me walking through the steps on how to do this using Desmos. So for example 1, we are going to want to find a linear regression model for a specific set of data. So here we're going to add item, go to table, and now we're going to add in our x coordinates, which are 4, 5, 6, 8, and 12. And now our y coordinates here, this should be 4.2, 4.4, 4.8, 5.1, and 5.7. Once we have this, we want to add a linear regression line. So we are going to hit add regression. And now it's already on linear. If you wanted to, you could change it though, but we'll keep it at linear for now. This should be our linear regression model, which is 0.185x plus 3.545 as a constant term. Now for part B. Using the linear model for part A, what is the predicted weight of a baby that is 10 weeks old? So looking at our x and our y variables, in this case they call it t and w of t, we want to find what is our y value when x is 10. And so to do that, what I would recommend is double click on this, copy it, and paste it in here, and now replace y with an actual function, f of x. It should be the exact same line, but what we can do here is now if we want to plug 10 into this equation, we can put f of 10 and get that it equals 5.395, which is our y value when x is 10. So that should be our answer for part B. Part C, we want to find the age now in weeks of a baby that is 5.3 kilograms, or at least an estimate of that. Here, this is a little trickier because we are given our y value and we need to kind of work backwards to find our x. So what we really want to see is what x value, so I'm going to put f of x here, what x value will make this function equal to 5.3 kilograms. So if we graph this, we now have two lines, and this is why we found the intersection points last class, because now we know a baby that is 9.486 weeks old will be, with our estimated, with our line of best fit, be 5.3 kilograms. All right, now example 2, this is giving us just 8 ordered pairs. We want to find what function type best models the data in the table, explain your answer, and write the equation of the regression model for the data in the table. I will say with these types of questions, it will either be linear or quadratic. And linear will typically be when it's strictly increasing or decreasing, and quadratic would be when the data goes up and then down, and that or goes down and then up like that. Those are going to be really the only two that you would see that you wouldn't be given the fact that it's like cubic or quartic or even linear quadratic. You wouldn't be given that data regression model beforehand. Example 2, we have a data table that provides 8 ordered pairs, and we want to find what type of regression would best model this. So let's take a look. Let's first add in our pairs into our table. So 0, 0.4, 0.9, 1.2, 1.7, 2.2, 2.9, and 3.4 as our x values. Now looking at our y values, we have 5, 10.6, 15.4, 17.1, 18.0, 16.5, 10.2, and 2.8. Once we have this, we can kind of zoom out if you want to and take a look. You can look and see here that probably quadratic would be the best, right? The points are kind of going up and then they're going down. You can also take a look at this table and see our y values are going up to 18 and then they kind of go down. When they go up and down like that, quadratic will always be the best line of best fit, right? Linear doesn't really match up, but if we do a quadratic, that is going to be the best. And typically, you won't ever see cubic be like the line of best fit. It's always going to be just quadratic in this case. All right, so once we have this, we know it's quadratic, and you can say the y values increase and then decrease, and then a regression equation should be this just from the table. So that should be your answer. You can either write down all the decimal places, that's fine, or round to at least 3. If you round to fewer, it would be like marked wrong on a quiz or a test. So just be aware of that. All right, let's try example 3 together as well. All right, so we are now given another table talking about vehicles available for sales in days since the beginning of a month, and we want to find a quartic regression. This is given to us directly in the problem, and we want to use a quartic regression. So first we're going to add a table and enter our y values here, which looks good. Now we entered our x. Now we're going to enter our y. So 62, 54, 49, 37, and then 41 here. And now we're going to add regression, and then we are going to add a quartic. So this fourth one, don't get confused with quadratic. Quartic should be the regression we want to use here. Here, obviously, our data points are a little off, or a little out of the screen, so let's zoom out just so we can see them. And this is going to be our quartic regression. Now, here, we don't need to write our equation or anything like that. What we want to do is we want to find what is our y value when we plug 29 into the quartic function. So what we can do is if you double-click this and then copy, now paste. Now, if you go all the way to the front of the equation, we could replace y with, we'll do v of x, right? And that is our function name. Now we can find v of 29 and get our answer here, which should be D 63.590. All right, now example 4, I'm going to walk you through this one step by step. This is going to be a short answer question that very similar or something like it, you will see 100% on the AP exam, and this will appear not only on your next test, but also on your semester summative as well. So be prepared for this type of equation, or this type of question. So let's talk about the setup real quick. Here we're given a table that gives the number of cars in the parking lot at a local store. When it opens at 8 a.m., there is only 4 cars in the parking lot. 5 hours later, there's 21 cars, and then 8 hours after the store opens, or 3 hours after that 5-hour time slot, there's only 14 cars left. The number of cars can be best modeled by a quadratic function, L, which means we will give you the fact that it's quadratic. Given by L of t equals A of t, or A times t squared plus B times t plus C, where L of t is the number of cars in the parking lot, t hours after the store opens. Question A will always ask you to write a number of equations to find the values for the constants A, B, and C in the expression L of t. Now here, this is not a hard question. Just be aware that this question wants you to write 3 equations. It does not want you to solve for A, B, and C. That's part 2. So what we're going to do here is take a look at our 3 points, right? We have 0, 4, we got 5, 21, and we have 8, 14. Now take a look at our equation. We have L of t equals A t squared plus B t plus C. Now let's plug these points in. But first, let's kind of translate this equation, right? We're not changing the equation. We're not adding anything or subtracting or multiplying. Just replace it with or write it in terms of x and y. So like y equals ax squared plus bx plus c. And now we have 3 coordinates that are xy pairs. So we can write 3 equations by just plugging in each coordinate into the equation. And the nice thing about this is there's no need to simplify. I actually urge you or beg you to not simplify your equations. Why? Because you don't need to, and it's easier for the reader to understand what you're doing, because if you make mistakes simplifying, it would be marked wrong. So here, our first coordinate is 0, 4. 4 is our y, equals a times 0 squared plus b times 0 plus c. Leave it like that. The next one, 5, 21. 21 is our y, equals a times 5 is our x value squared, plus b times our x value is 5, plus c. And then third, we have 8, 14. So 14 is our y, equals a times 8 squared, plus b times 8, plus c. And this is our answer. So that would get you full credit on an AP exam. All right, step number 2, we want to find the exact values for A, B, and C as decimal approximations. So this one does require the use of Desmos, which I am about to walk through now. Now, to find the values for A, B, and C as decimal approximations, this kind of has nothing really to do with part AI. So what we're going to want to do is do a table, enter our 3 data points, so 0, 5, and 8 as our x coordinates, and then 4, 21, and 14 as our y coordinates. Then we will add a regression. And here, based on what the story gave us, we're going to want a quadratic regression, right? That quadratic function is what they said is best modeled. So there. And now this should be our quadratic regression, in which case, to answer the question, A is going to be negative 0.717. Remember, round to 3 decimal places. B should be 6.983. And C is just going to be 4. You don't have to put 4.000. You can just write 4. That's totally fine. And that should be our answer for part AII. All right, so part BI, or use the given data to find the average rate of change in the number of cars in the parking lot in cars per hour from 5 to 8. Express your answer as a decimal approximation. So remember, this is meaning they're looking for 3 decimal places. Show your work that leads to your answer. So this part actually has nothing to do with the quadratic equation above. So get that quadratic equation in your brain and kind of forget about it for now, right? We'll go back to that later. But here, you just want to find the slope, right? The average rate of change is another word for slope. So find the slope between 5 and 8. So our 2 coordinates are 5, from the table, 21, and 8, 14 from the table as well. Right? Once we have that, we're going to plug it into the slope formula. So remember, slope is equal to y2 minus y1 over x2 minus x1. Once we have this, plugging it in, 14 minus 21 over 8 minus 5 should give us negative 7 over 3. Now, even though this is our answer, we remember that they asked for decimal approximations, so we do not want to just leave that as our answer. That would technically be marked as wrong. What you want to do is convert this into a decimal. So if you throw it in Desmos or use a calculator, you should get negative 7 over 3 is negative 2.333. And so if you do not give your answer as that, it would be marked wrong, even if you say negative 7 over 3, because it asks for a decimal approximation. In terms of your work, they would want to see that fraction set up right there. We're going to use this in our next part, part BII, which is use the average rate of change found in part 1, which we got to be negative 2.333, or even negative 7 over 3 if you want, to estimate the number of cars in the parking lot at time t equals 7 hours. Show your computations that lead to your answer. So here you are not going to use that quadratic function. We're going to use that kind of a straight line between those 2 points. So here, if we kind of imagine 5 and 8, and then let's say you got 14 and you got 21 here, at 5, 21 and 8, 14, right, we found a straight line between those 2 points. We want to figure out what is our y value at 7, right? What is this value going to be? So start at the point 5, 21. What our slope means is every time we move 1 unit to the right, we are actually moving down 2.333 units. That is, by definition, what slope is, which is why we tried to find it in part 1, or I. Now, if we want to get from 5 to 7, moving 1 unit over to the right, we're now already at 6, and then moving 1 more unit over to the right, we are going down another 2.333, but we are at 7. So how do we know our y value? Well, we started at 21, we went down 2.333, and we did that twice because it's 2 units from 5 to 7. So here we're going to multiply that by 2. This should be 21 minus 4.666, which then, once we do that, you should get an answer of 16.333, which is going to be our final answer there. This is typically, you can be done by taking your coordinate of your earliest point, right? So in this case, it's 5, and we want to take our y coordinate of 5. So y coordinate of early point, and then you want to do plus your slope, in which case our slope was a negative number, times distance between 7 and 5 in this case, between our t value, so we'll call that our t value, and early x coordinate. And this would always give you our the correct answer for this type of question. All right, so for part B, III, this question is a lot to take in and one of the most difficult questions on the AP exam by far. Only 1% of students actually got this question correct on last year's AP exam, so let's go over this step by step. All right, so A of t represents the estimate for the number of cars in the parking lot using our slope found in part BI. So let's take a look at this line here. This is going to be our A of t, which is basically, we used that straight line. I graphed it here for you just so you can see what it looks like visually. And that is going to be what A of t is the estimate with that slope being the deciding factor of how we got that line built. All right. So the average rates of change found in part BI, or A of t, is another word for that secant line that runs through both points at 5 and at 8. Remember, a secant line is just a line that runs through 2 points. So that is simply what a secant line is. For A of 7 found in part BI, it can be shown that A of 7, which is right here, so this is A of 7, of 7 is less than L of 7 here, which this is going to be L of 7 because L of t is going to be our quadratic function. So here, L of t is our quadratic function there. And that was what we found in part AII, and so that's why I have it graphed here using Desmos. So that's that black line there is model L. We are simply looking in between 5 and 8. So we can kind of have tunnel vision now and only focus on this graph in between t equals 5 and t equals 8. So even though my lines may not be perfectly straight, this is the area that we're focused on. We are not focused on anything else that's going on in this graph here. So we can kind of block out all of that because it's irrelevant right now. All right. And then explain why in between 5 and 8. Basically, the black line is going to be above that straight line, that purple line. Your explanation should include a reference to the graph of L, which is the quadratic, and its relationship to a of t. And so what we want to know is whether the straight line will be higher or lower than the quadratic equation. Luckily, they already gave that to us, where they basically say a of t is going to be less than L of t. So it's going to be the straight line is always going to be lower than the quadratic in between 5 and 8, right? After 8, we see the straight line actually gets above the quadratic, but we're not worried about that right now. And so, as we can see, some things that we want to point out is the quadratic, or L of t, is concave down, which means from 1.1, the rate of change is decreasing, while the rate of change of the straight line, or a of t, stays the same. Handwriting is not the best, but that's okay. Stays the same because it's a straight line, right? All linear lines have the same slope. Because of this, the black line will always be above the purple line between those two endpoints, 5 and 8. All right? So in my answer, what I would do is I would just at least sketch a general graph, maybe like this. I would sketch 5, I would sketch 8, and then just show how it looks graphically. So show that that secant line is below the quadratic function, and you can always sketch the general shapes and kind of get your answer or check your answer this way. Now, in terms of answering the question, I would also, besides that little portion of the graph, I would write up an explanation. And so I would word my answer as such. This is the answer that came from AP. You don't have to memorize all of this, so just pay attention for the next minute or so. The estimate A of t is the y-coordinate of a point on the secant line that passes through 521 and 814. So here, if you think about it, right, 521 and 814, that was that straight line, and then that was the model L, and then this is A of t. And so A of t is just going to be the y-coordinate that passes through there. All right? Because the graph of L is concave down in between 5 and 8, the secant line is below the graph of L on the interval from 5 to 8. And that's true, right? The secant line is always below L in between 5 and 8. Therefore, the estimate using the average rates of change A of t is less than the value of L of t for any number between 5 and 8. Now, I know that's a lot. You don't have to have that all in there. However, I'm going to explain what I'm going to be looking for when I grade your test, I grade your homeworks, I grade your semester summatives, and I grade AP exams this summer. So to get this point, you must include the fact that the quadratic equation, the graph of L, is concave down, or you can say the rate of changes of L is decreasing, right? Because we learned that these two are essentially equivalent. If the rate of change is decreasing, that's another way of saying it's concave down. So as long as you mention one of those two things, that's halfway there. The next thing that I would be looking for is just for you to reference the fact that you found a secant line in between 5 and 8, or you used a linear function, right? You basically formed a linear line with the points 5, 24 and 8, 14. So you would need those exact endpoints. If you don't have those, it would be marked as wrong, that provide placement of the line. And so that is why I kind of like drawing out that little diagram as well, because if you don't necessarily cover the secant line in there, if you can show it visually, that is a kind of a safety net for you to still get partial credit for this question. But this is a very hard question to answer, and so those are the two things that I will be looking for. Obviously, I want a little bit more of an explanation than you just saying L is concave down, there's a secant line between 5 and 8, right? If you just have that, you probably won't get full credit. So Make sure that you explain your reasoning as well, but that is what I will be looking for. All right, and then part C, here we are given something about the domain. So here's a video of me explaining this. All right, so our final part, part C, this is a question asking about domain or range, but where we have to use Desmos as well. So the Model L is an appropriate model to make predictions about only if the number of cars in the parking lot is at least 0. This makes sense, right? We can't have negative cars in the parking lot. And so, what's the largest value of t? What's our largest x value for which the model is appropriate? So if we take a look at our value, right, our model starts with 4 cars in the parking lot. It then increases and then decreases, and then around here, this 0 is where it will now start not being appropriate because we have negative cars in the parking lot and that doesn't exist. So what we're going to want to do is, looking at this line, you just want to hover over that 0 and find your x value of that 0. So at t equals 10.287, rounding to 3 decimal places, this is going to be where our domain will end, right? That's our endpoint of our restricted domain. And so our domain should be restricted to 0, which is less than or equal to t, which is less than or equal to 10.287. And this is because the 0, that is the 0 of the quadratic equation and where we go into negative t values there. All right? And so that should be it for that long FRQ question. If you have any questions, please come see me in office hours, and I will see you guys later. Thanks.